Okay, so in this video, we are going to talk about the first section of our new unit. So our fourth unit is Unit 4, or the periodic table. And in this, we're going to explore how the elements are organized. And we're going to talk about a bunch of different trends that are represented on the periodic table and what makes it such a powerful tool in chemistry. So this is going to be in pages 4 to 7 in your new packet. Okay, so starting out on page number 4 with periodic law. So the story begins in 1869 when Dmitri Mendeleev arranged the known elements in order by their atomic mass. Okay, so that's just the mass of an atom of those elements. And him and his students studied this and organized it and found that there were special kinds of trends that related to conductivity, ductility, malleability, and a bunch of other stuff that started to come out or come up when they arranged it by their atomic mass. So the atomic mass on your periodic table is that number that is like the decimal place number. Okay, so then over time in like 1913, another guy came along, Moseley, who discovered that it's a better order to arrange them by their atomic number instead, which is by their number of protons. Because there was some inconsistencies with the original, but now like it kind of shows those trends a little bit more clearly. Okay, so again, that atomic number, like we talked about in Unit 1, is a number of protons. So that's why on the periodic table, we start at the top left with 1 for hydrogen, 2 helium, and then it goes 3, 4, 5, 6, 7, 8, 9, 10, right? So the entire periodic table is organized in this way, with the lowest or the first atomic number with atomic number 1 up here on the left, and then kind of as you go either across the row or down this column, those numbers or the atomic number is going to increase, which is just the number of protons that each atom of an element has. Okay, so that's just the first trend. So the periodic table is arranged in order of this increasing atomic number, where we increase going to the right and increase going down each group or each column. Okay, so now we're going to talk about what these columns and these rows are actually called on the periodic table. But the first term is period. So a period are those horizontal rows. So they go left to right. Okay, they go across. And they are numbered 1 to 7. So on your periodic table, if you take a look at the periods or these rows, you see a label on the left hand side. It says 1, 2, 3, 4, 5, 6, 7. So these are your 7 periods or rows on your periodic table. So you can think of the periods as like theater seats. So rows go across like horizontally. Over here, you'll notice that there's like these 2 chunks that are down at the bottom of your periodic table. And these are your rare metals, but they go kind of in this space here, but we kind of just put them out to the bottom so it kind of like fits nicely. So the periodic table isn't all like long and wonky. So it just kind of makes it easier to understand and look at. So that's why these are like this top group here is a part of, or top row, I should say, is a part of period 6, and this bottom row is a part of period 7, but we just kind of kick them off to the side. Okay, so periods are arranged to represent the number of energy levels that that atom of a certain element will have. So period 1 will have 1 energy level, 2 will have 2, 3 will have 3, 4 will have 4, 5 will have 5, 6 will have 6, 7 will have 7 energy levels. Okay, so those are those energy shells. So we've looked at this before, but this is just like a close-up of periods 2 and 3 on your periodic table. So those start with lithium in period 2 and sodium in period 3. But you'll notice that as you go across and you look across, that in period 2, all of those elements are going to have 2 energy levels or 2 energy shells or electron shells. So lithium its electron configuration is 2 1. Okay, so there's two numbers there. That's telling us that there's 2 electrons in the first shell, 1 electron in the second. Okay, and beryllium has like a similar thing where it has a specific number of electrons in the first shell and a specific number of electrons in the second. Okay, so a total of 2 energy levels or energy shells in all of the elements in period 2. But then if we compare that to period 3, that's now going to give us 3 energy levels for all of those elements that are in that row or in that period. And that will continue on for like periods 4, 5, 6, right? So it just corresponds, the period numbers correspond to how many energy levels that those elements will have. Okay, so now the other term is the groups. So groups go up and down or vertically. And we can refer to them as columns. So if you think of like a building, and you think of like these pillars here, okay, those are like columns. So they're going up and down, they're going vertically. So those are what your groups are. So groups will be numbered 1 to 18. Sometimes they're different on different kinds of periodic tables. The one you have has it labeled 1 to 18, but sometimes when you see it, sometimes it'll label this one that's yellow over here for 3, and then it'll kind of go to 8. It just kind of depends on what periodic table you are looking at. However, the groups are arranged in a little bit of a different way, but down a group, all of these elements are going to have the same number of valence electrons. So these valence electrons are super duper important. We've talked about them before. So these are the electrons that are in the outermost energy level of an atom. Okay, and because everything down these groups will have have the same number of valence electrons, means that they will have similar chemical properties. So in group 1, for example, so this would be group 1 right here, all of these elements in group 1 will have 1 valence electron, 1 outermost electron. So that means that all of these are going to have these similar chemical properties. Okay, group 2 is going to have 2 valence electrons. They will have similar chemical properties to each other, and so on. Okay, this is just a screenshot of group 1 specifically. So the first group, the column all the way to the left-hand side, and we see lithium, sodium, potassium, and rubidium going down. If you look at that outermost electron that's highlighted in yellow here, okay, they all have 1 valence electron. Okay, they have 1 valence electron or outermost electron within their atom, or within their atom on the outside of the nucleus. So because of that, all these guys are going to have similar chemical properties to each other. Okay, so this is just reiterating the same thing. So the groups going up and down are going to have the same number of valence electrons, which means they're going to have these similar chemical properties. Okay, and then we can also classify them further, which we'll go into right now. Okay, so that first group or that first column, which is shown over here, are called the alkali metals. So alkali metals can be lithium, sodium, potassium, rubidium, cesium, and francium. So going down here. The only exception is hydrogen, okay, which is not an alkali metal. That's why on your periodic table, hydrogen kind of sits by itself, okay, like above group 1, because it still has 1 valence electron. However, it doesn't have the same properties as those alkali metals. So alkali metals are super duper reactive. They're very reactive. They're not found in the elemental form typically, which means that they like to react with other atoms. They like to bond and make different compounds and things like that. Alkali metals will always have that 1 valence electron or outermost electron, which means that they typically are going to have a +1 charge. Metallic character is going to increase down the group, so meaning when we go from the top to the bottom and we go down, the metallic character of those elements are going to increase. They're going to have strong exothermic reactions with water, so that's kind of like what this very reactive is talking about. So remember that exothermic means that energy is being released. Okay, releases energy. So when these alkali metals like solid lithium or solid pure sodium or pure potassium is mixed with water, it will kind of create this really strong exothermic reaction that's going to release a lot of heat. So that's what's shown in this picture here. They must have dropped one of these alkali metals mixed with water, and it kind of produces like this a lot of heat and kind of like this explosion type thing. I'll show you a demonstration of this in class though. Okay, group 2, which is the second column, are called the alkaline earth metals. So alkaline earth metals are still pretty reactive, just not as much as those alkali metals though. Alkaline earth metals, because they're in group 2, are going to have 2 outermost electrons or valence electrons, and they will typically have a +2 charge because of that. So alkaline earth metals, or alkaline means base. So when we talk about acids and bases, we have a whole unit on acids and bases. We'll talk about specifically what a base is, but these alkaline earth metals tend to form bases. So that can be any of these guys here, which are all in going down this group 2. So alkaline earth metals are like calcium carbonate. So that's what chalk is made of. So we have that calcium, which is the alkaline metal. And also another example is like the sparklers, you use on 4th of July. They're commonly made out of magnesium, which is an alkaline earth metal. So just some examples for you. Okay, so groups 3 to 12 are called the transition metals. So that's like this kind of big hunk here, and that also includes your rare earth metals that are down at the bottom. So your transition metals kind of vary with their properties and their valence electrons and things like that. However, they tend to form these colored compounds in solutions, which you can see down here. And they're typically going to be able to have various charges depending on what else they're reacting with. So an example here is manganese. So if you were to find manganese on your periodic table, it's somewhere kind of over here. Manganese at the top right, if you were to look at those oxidation states, that's like kind of like what your charges are. You can see that there's multiple possible charges for it. So we can have a +2, a +3, a +4, a +7. But again, it just kind of depends on the situation or what else that manganese is kind of reacting with and forming compounds or solutions with. So these examples are showing how these transition metals are forming these colored compounds. So this one on the left is copper sulfate. So copper is a transition metal. It forms like this really bright blue compound. Iron sulfate, iron is a transition metal. In this case, it's going to form like this aqua blue color. And then we also have this cobalt chloride, with cobalt being a transition metal, and it forms like this cool purple color. Okay, so now we're skipping all the way to group 17, so the second to last group, which is all the way over here. Okay, so group 17 are called your halogens. Halogens are gonna be the guys that form these diatomic molecules, and we'll go over what a diatomic molecule is in a second. But your halogens are mostly gonna have a -1 charge, though in other charges can be possible depending on the case. Your group 17 is going to have 7 valence electrons. They are also going to be very reactive, and these are just those halogens in group 17 that are listed. So before, when we talked about the group 1, the alkali metals being very reactive, your group 17 are also going to be another group that is super reactive. So it all has to do because the fact that your group 17 has 7 valence electrons, and your group 1, your alkali metals have 1 valence electron. But in the next video, the next section, we'll talk about metals versus nonmetals and what they actually are. But your halogens are the very reactive nonmetals. Whereas like your alkali metals, of course, are going to be your very reactive metals. Okay, so just a refresher on a diatomic molecule. So remember that the prefix di means two. Okay, so it's two atoms that make up this molecule. So it's a molecule that's composed of two of the same atoms. Okay, so why do they like to do this? It's because halogens have 7 valence electrons, and they only need one more to reach the stable octet that they want. Okay, so the stable octet we've talked a little bit about before. So this is kind of like that happy number that all atoms want to obtain in order to be stable, in order to be happy, we say. So when there's 8 valence electrons, so 8 on the outermost energy level in the outermost shell, that is when they're the happiest. And that's why things bond, because we just saw in like the other groups how different elements or atoms of that an element will have varying numbers of valence electrons. They have 1, they can have 2, they can have 3, 4, 5, 6, 7. Okay, all of those want to bond with other things in order and to create compounds in order to achieve this 8. Okay, so because halogens just have this 7 and they only need one more, all they need is one more electron to reach the stable octet. So therefore they're going to react very kind of strongly with things, very aggressively. They really, 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 really want to achieve that stable octet, and they're super close to it. Okay, so why these diatomic molecules form is because if each of them have 7 valence electrons, okay, they're able to kind of just like share one more with each other and then be happy. So that's why they like to stick together. So this is just another picture of those diatomic elements, so that Brinkelhoff that I've told you about in class. So all those elements like to form these diatomics. And this is just a cute little cartoon kind of like explaining that concept. So here we have a very unhappy element, an atom of an element. So let's say it's fluorine. So this is a fluorine atom. And that fluorine atom only has 1, 2, 3, 4, 5, 6, 7 valence electrons. Okay, it does not have a full valence shell of 8 electrons, so he's very unhappy. Okay, so what's he gonna do? He's gonna find a buddy, and him and his buddy are gonna share that 8th electron, so now they're both happy. They both have that stable octet. Okay, so that's why these diatomic molecules will form. It's because they're typically will have like 7 valence electrons. They're super close to having that stable octet, so they're just buddy up with another one of the same and share that 8th valence electron to have that octet. Okay, so that brings us to our last group, which is group 18. It's also super important. We've talked about this quite a bit as well. So your group 18, or the last group, the group that's all the way to the right, or the column all the way to the right on your periodic table, called your noble gases. They're also known as inert gases because they are very, very, very stable. It says here except for xenon in rare cases, but for the most part, all of these gases are going to be very, very stable. They're very stable because they already got that stable octet. Okay, so they don't need any more electrons from anything else. They don't want to bond with any other atom. Okay, they're happy the way they are. So that's why they're just very stable. They're very unreactive, and because of this, they're gonna have a 0 charge. They're not gonna have any charge. Your noble gases are what is gonna form those monoatomic substances. So like helium, neon, argon, krypton, etc. All those are gonna form those monoatomics. So remember that mono is different from di because mono just means one. Okay, so they're just going to exist as a single element by itself. Okay, so I want you to redraw this picture again. I know we went over it a few times in class, but this is just showing the difference between the diatomic molecules, or diatomic particle diagram, and the monoatomic. So di, again, means 2, and we can see here that it just means that 2 of the same atoms are going to be chemically bonded together. They're going to stick together. So these are going to be your Brinkelhoff or your halogens. which has typically will have 7 valence electrons. So they just like to buddy up with another friend of the same type of element so that it can they can both be happy and be stable like that. Whereas your monoatomic particle diagrams will look like this, where we have these particles just kind of freely floating by themselves. They don't want to be bonded to anything. These are going to be your noble gases because they're super duper happy already. They have 8 valence electrons. They don't want any more. They're cool how they are, right? They don't want to bond with anything else.